suspension bridges are among humanity's greatest engineering achievements. Structures so large they defy belief, yet so graceful they seem to float above the water. But behind every elegant curve lie the strongest cables ever created. Cables that carry the weight of entire roadways. Cables that resist hurricane winds, earthquakes, corrosion, and decades of relentless stress. Cables that allow millions of people to cross rivers, bays, and oceans every single day. Today, we're stepping inside one of the most advanced steel cable factories in the world, a place where raw metal transforms into precision-engineered strands powerful enough to hold up cities. Later in this film, you'll witness the moment steel wire is pushed to its breaking limit, revealing exactly how strong suspension bridge cables truly are. Every steel cable begins with one of the strongest materials on Earth, high-carbon steel. Inside the factory's blast furnace, iron ore, coke, and limestone melt together at temperatures above 1,500 degrees Celsius. Alloy elements like manganese, chromium, and vanadium are added to give the steel greater strength and toughness. The molten metal flows into continuous casting machines and emerges as glowing billets, pure cylinders of steel destined to become suspension bridge wire. But before any billet is approved, it must pass spectrometer analysis. Hydrogen levels must be low to prevent cracking. Carbon content must be precise, usually between 0.6 and 0.85%. The slightest deviation can weaken the entire cable. Only the purest billets go forward, because a bridge cable's strength begins right here. In the rolling mill, each steel billet is reheated to over 1,100 degrees Celsius. Still glowing yellow-white, it enters a series of rollers. With every pass, the billet stretches longer, thinner, and stronger. Within seconds, it transforms into a long steel wire rod, just 5 to 10 millimeters thick. Rolling speeds here can reach 60 to 100 meters per second, faster than a race car. As the rod cools, lasers monitor its diameter to within fractions of a millimeter. Thermal cameras watch the temperature profile to ensure proper grain structure. When the rod finishes its journey, it's wound into enormous coils, each weighing over a ton. These coils are the raw material for the world's most powerful suspension cables. Before the rods can be drawn into fine wire, they need to be perfectly clean. They enter a long pickling line where acid baths remove scale and impurities. The rods are rinsed, neutralized, and then coated with a thin layer of lime or phosphate, a lubricant that reduces friction during wire drawing. This microscopic coating, only a few microns thick, is essential. Without it, the steel would overheat and fail during the next stage. It's a small detail. But in engineering, small details make the difference between strength and catastrophe. Now comes one of the most remarkable transformations in the entire factory: cold drawing. Each rod is pulled through a series of tungsten carbide dies. Every die reduces the diameter a little more. As the steel stretches, the grain structure aligns, and the metal becomes dramatically stronger. The thinner the wire becomes, the higher its tensile strength. By the time it reaches its final size, usually between 4 and 7 millimeters, its strength can exceed 2,000 megapascals. To put that in perspective, this steel is stronger than the armor on a main battle tank. Cooling systems control the heat buildup. Lubrication systems feed just enough coating to prevent die wear. After passing through multiple dies, sometimes 10 or more, the steel emerges as high-strength wire, perfectly smooth, perfectly round, and stronger than almost any other metal product in the world. A single wire is incredibly strong, But a suspension bridge cable must be flexible as well. To achieve both strength and flexibility, factory engineers twist multiple wires together into strands. A 7-wire strand is common. A 19-wire or 37-wire strand is used for larger bridge designs. Inside a stranding machine, dozens of wire spools feed into a rotating cage. The cage spins while tension control systems keep each wire perfectly aligned. The process must be flawless. If one wire carries more load than the others, it can fail prematurely. Every strand is monitored using sensors and cameras. The helical twist, called the lay length, is carefully controlled to ensure even load distribution. The result, a flexible, high-strength strand that will one day support thousands of tons. In a full-scale suspension bridge, cables are actually spun on site. Thousands of wires pulled across the towers and bundled in midair. But inside the factory, engineers simulate and prepare these massive bundles. Hundreds of strands are grouped together. Hydraulic presses compact them into a perfectly round shape. Internal lubrication is added to prevent corrosion over decades of service. Some of the largest cables in the world can contain over 150,000 individual wires, while each one essential. The compaction force here can reach 200 to 400 tons. When complete, the cable feels like a single piece of steel, despite containing thousands of parts. This structure is the backbone of any suspension bridge. Steel may be strong, but corrosion is relentless. To protect the wires, they undergo hot dip galvanizing. They are lowered into molten zinc, heated to around 450 degrees Celsius. The zinc bonds to the steel, creating a protective barrier that can last for decades. For marine environments where bridges face salt spray and humidity, polymer or epoxy coatings are added. These coatings are applied in controlled chambers to achieve precise thickness. Every layer of protection adds years, sometimes decades, to a cable's life. Without this step, even the strongest steel would eventually fall to rust.
Down slow, steady as she goes. We are aligned for final placement.
Roger that, setting it down.
As is Gotham. To guarantee safety, each batch of wire and each finished strand must pass rigorous testing. In the Tensile testing room, a machine grips both ends of a steel wire. Hydraulic pistons begin to pull. Slowly at first, then harder and harder. The wire stretches. Tension builds, until finally, it snaps. High-speed cameras capture the failure. Sensors record force levels, elongation, and break patterns. A properly made wire should reach breaking strengths of 1,600 to over 2,000 megapascals. Anything less, and the wire fails certification, because on a suspension bridge, one weak wire can put thousands of lives at risk. Before cables leave the factory, they are wound onto giant spools, some weighing more than 50 tons. Each spool receives a unique serial number. Every batch includes documentation of wire chemistry, tensile results, galvanizing thickness, stranding specifications, international compliance standards. Laser engraving and digital records ensure that every cable can be traced for decades. These cables may one day travel across the ocean, be lifted onto bridge towers at Timeti track connection, and become part of a structure built to last more than 100 years. Suspension bridges are more than concrete and steel. They are symbols of connection, linking cities, nations, and people. And at the heart of every bridge, hidden inside massive cables, are thousands of wires forged in fire, strengthened by pressure and protected by engineering. From molten steel to high-strength wire to massive cables stretching over entire oceans. This is how suspension bridges stand tall, held up by the strongest cables ever made. And this is inside manufacturing.